There is a spaceship that could fly over the pole of the sun and look down on our own star, something no machine has ever done. It would not crawl there over decades like our probes. It would get there fast, and it could carry a crew, not just a sensor. The wild part is that we are not waiting on some future invention. The machine was designed, tested, and proven to work, and then we buried it because the way it flies is genuinely terrifying. It doesn't burn fuel. It rides nuclear bombs. Stay with me because by the end, you're going to have to answer a real question. Would you climb aboard a ship that flies by dropping atomic bombs out the back and surfing the explosions? Because that's not science fiction. That was a real American project with real engineers, real money, and a real working model. It was called Project Orion. If you saw the video on why we are trapped on a flat plane, you already know the problem. To climb out of the disk the planet shares straight toward the pole of the sun, you need a change in speed so enormous that our chemical rockets cannot even dream of it. We are prisoners of a flat map. Going up is almost impossible. But in the 1950s, a group of brilliant, slightly mad scientists looked at all that wall and refused to accept it. They did not want to burn hydrogen and oxygen like everyone else. They wanted to stack atomic bombs behind a giant steel plate and ride the shockwaves straight up and out. It sounds insane. It was also the only thing we have ever designed that could truly conquer vertical space. So let's start with the simplest question of all. Why can't our normal rockets just do this? To understand why anyone would seriously propose riding bombs, you first have to understand why the normal way fails so badly. So let me give you the one number that controls everything in spaceflight. It's called delta V. Think of it as a budget of speed. Every rocket is born with a fixed amount of speed it can ever spend, set by how much fuel it carries and how fast that fuel shoots out the back. And here's the cruel part. Climbing out of the flat plane of the planet straight up toward the pole of the sun is one of the most expensive things you can possibly buy with that budget. It's not a little expensive, it is brutally, almost absurdly expensive. Why? Because everything we launch is already moving sideways at enormous speed, riding along with Earth or around the sun. To go straight up out of that sideways motion, you first have to cancel a huge chunk of it, then add fresh speed to climb. A chemical rocket simply does not carry enough budget to do that. Let me make it concrete. To change your path by 90 degrees, to truly fly over the pole instead of around the equator, a rocket like the Falcon Heavy would have to be almost entirely fuel. A tower propellant the size of a skyscraper, just to push a single small probe up and over. The payload would be a pebble riding an ocean of fuel. That's not a spacecraft. That is a fuel tank with a sensor taped to the front. This is the wall. Chemical engines are too heavy and too slow, and the fuel they burn gives back too little speed for the price. We have squeezed them about as hard as physics allows. So the question becomes obvious. If burning fuel can never give us enough speed, what could? What kind of engine carries enough raw energy to break us out of the plane entirely? In the 1950s, a few people had an answer that still sounds insane today. Before we get to the bombs, there is a trick even a normal rocket can use to cheat the wall a little. It is one of the strangest, most counterintuitive ideas in all of physics. And once you see it, you will never look at a rocket engine the same way again. It is called the Oberth effect. Here is the puzzle. Take two identical burns. In the first, you fire your engine out in deep space, far from any planet, and you get a certain boost. In the second, you fire that exact same engine burning the exact same fuel, but you do it while driving fast and low past a massive object like the sun. The strange truth is that the second burn gives you far, far more final speed than the first one. Same fuel, same engine, wildly different result. How can that possibly be? The answer is about speed at the moment you burn. When you dive deep toward the sun, its gravity drags you to tremendous velocity. You are moving fastest at the closest point, what we call the perihelion, the bottom of the dive. And here is the key. The energy you get from your fuel depends on how fast you are already going when you burn it. The faster you are moving when you light the engine, the more useful energy that same fuel delivers. So, you do not burn your engine out in the calm of deep space. You wait. You let the sun pull you into a screaming dive, and at the very bottom, at maximum speed, you fire. The fuel you burn at that instant is worth several times what it would be worth anywhere else. The numbers are genuinely shocking. In a deep dive past a giant planet like Jupiter, a burn of just 5 miles per second at the bottom can turn into a final gain of nearly 14 miles per second once you climb back out. The same fuel used in the right place multiplies its effect by more than 4 times. It feels like stealing energy from gravity itself. Now, connect this back to our problem. To launch up and out of the plane over the pole of the sun, you want every scrap of speed you can get. So the plan becomes almost poetic. You dive down toward the sun. You whip around it at the bottom at staggering speed. You burn hard at that exact moment, and you get flung up and out of the plane like a stone from a sling. The Oberth maneuver is how you turn a dive into the sun into an escape above it. But even with this trick, a chemical rocket still does not have enough budget. To really use it, you need an engine with far more raw power, and that is where the bombs come in. So, in the late 1950s, at a company called General Atomics, 2 physicists named Ted Taylor and Freeman Dyson asked a question that everyone else was too sane to ask. We already have the most concentrated source of energy humanity has ever built. It is the atomic bomb. So why are we trying to fly on chemistry when we could fly on nuclear explosions? Here's how Orion actually works, and it is shockingly simple. At the back of the ship, there is a massive thick plate of steel called the pusher plate. Behind the ship, you drop a small nuclear charge, a bomb, and detonate it a short distance away. The explosion slams into the pusher plate and shoves the entire ship forward. Then you drop another and another. One bomb, then the next, detonating behind you again and again, each blast kicking you faster. You're not burning fuel. You're surfing a chain of atomic explosions. Your first thought is the obvious one. The crew could be turned to jelly. The engineers thought of that. Between the pusher plate and the crew sat enormous shock absorbers, giant pistons and springs designed to smooth each violent kick into something a human body could survive. The plate takes the brutal punch. The shock absorbers stretch that punch into a firm, steady push. And here is what makes this worth the madness. The numbers are staggering. The original design was a beast, a ship weighing 10,000 tons, standing as tall as a skyscraper, with a pusher plate over 130 feet wide, dropping a small nuclear charge roughly once every second. It could carry not a tiny probe, but a crew of 150 people and thousands of tons of cargo. Think about what that means for our problem. Every other plan to reach the poles of the sun involves a tiny robotic probe and a journey of decades. With Orion, that same trip would take months, and instead of a lone instrument, you could send a laboratory, a crew, a small outpost. Orion is the only design we have ever had with enough raw power to truly use that dive and slingshot trick and fling real mass up out of the plane. It was the key to vertical space. So why are you not watching Orion ships launch today? Why did this die? 2 reasons, and they are both serious. The first is fallout. The original idea was to launch this thing from the ground, which means setting off dozens of nuclear bombs inside our own atmosphere, one after another, raining radioactive particles down on the planet every single launch. The second reason is the one that actually killed it. In 1963, the major powers signed a treaty banning nuclear explosions in the atmosphere, in the ocean, and in space. With one signature, Orion became illegal almost everywhere it could fly. The following year, the project was shut down. The most powerful spaceship ever designed was strangled by the very thing that gave it power. Now here's where it gets interesting again, because the dream never fully died. It just went quiet, and it changed shape. Modern engineers learned the lesson of Orion. You do not need to set off open nuclear bombs to use the atom. You can keep the reaction contained inside a reactor. The same basic idea as a nuclear power station, and use that heat to drive a spacecraft. There are 2 main flavors of this, and you should know the difference. The first is nuclear thermal propulsion. A compact fission reactor heats a propellant like hydrogen to ferocious temperatures and blasts it out of a nozzle. It works like a chemical rocket, but because the reactor runs so much hotter and more efficiently, it can be roughly 3 times as efficient as the best chemical engines. The second flavor is nuclear electric propulsion, where a reactor generates electricity to run highly efficient ion engines, sipping propellant slowly but pushing for years on end. Neither of these is as wildly powerful as riding open bombs, but they are real, they are legal, and recent programs have come close to actually flying a test reactor in space before being paused. The point is this: the contained, careful descendants of Orion are how we might finally get the raw, sustained power to do what chemistry never could: climb out of the plane, dive past the sun, and fly over a pole. Which leaves us with a genuinely uncomfortable question. We have always had a deep, instinctive fear of nuclear power in space, and after the history of bombs and fallout, that fear is understandable. But that same fear is part of what keeps us pinned to the flat disk we were born on. So how much risk are we actually willing to accept to break out of our two-dimensional prison? So step back and look at the whole strange story. The power to conquer the up and the down is not science fiction, and it is not a problem we still have to solve. In its boldest form, the answer has been sitting in a drawer for about 70 years, fully designed with a working model that flew. We left it there mostly out of fear. Some of that fear was wise. Some of it may be the only thing standing between us and the rest of the solar system. Which brings us back to the question I promised you at the start, and now you actually have the knowledge to answer it. There are 2 futures on the table. In one, we stay safely on the flat disk forever, with our gentle, clean chemical rockets, never quite able to climb out, watching the vertical sky we can never reach. In the other, we accept real risk. We ride the atom, and we see the galaxy from an angle no human has ever seen, from above and below the plane that has always trapped us. So tell me in the comments, would you stay forever on the safe, flat disk, or would you climb aboard a ship that flies by riding atomic bombs to see the sun from above for the first time in history? I genuinely want to know how many of you would actually get on that ship. The argument about Orion has been quiet for 60 years. Let's start it again right here. I'll see you in the comments and in the next one.